Recording. All right, so we continue today the elements of linear algebra. Let me briefly recap what we discussed last time. Let me change my color to, let's say, yellow. So when we talk about linear algebra, right, the first concept, the first object we have to introduce is the concept of basically linear space. We denoted this linear space by V, capital, and we say that linear space is a space of vectors. For example, any vector A, any vector B here, and we say that we can sum up these vectors, two or many of them, and we can also multiply the vectors by some scalars. The scalar can be real valued or imaginary valued or complex in general. Then we introduce the concept of linear independency of several vectors, like shown here in this blue frame. Alpha A vector plus beta B vector not equal to 0. So this is definition of two linearly independent vectors. If this expression is equal to 0 for some particular alpha and beta, then the vectors A and B are dependent. So simply put, this linear independency says that for our space, we can find a number of vectors that cannot be expressed in a combination of other vectors. For example, in our 3D space, three-dimensional space, we usually introduce x, y, and z, right? X, y, and z, x, y, and z, coordinate system, and why 3, right? Why not 2 or 4? Because for our space, the space is three-dimensional, our physical space, there is a maximum amount of free vectors that are linearly independent or orthogonal. For our space, they are, you can say they are orthogonal. And this free coordinate system, these three axes, these three vectors are enough to express any other vector in this space. Let's say we have a vector of velocity of some particles, and this vector can be expressed in terms of its projection to other coordinate, to these orthogonal vectors. That's why we introduced this concept of linear independency. Very good. So then the number of linearly independent vectors, n, is the dimension of our space. And this n can be 1, and then space is one-dimensional. It can be 2, it can be 3. Like for our space, this n is three-dimensional space. It can be any number, any number, even infinity, like a general space, vector space can be of infinite dimensions. And in fact, in quantum mechanics, we will see this today. People work with Hilbert space, which is initially of infinite dimension. But in reality, in our calculations, we don't work with infinities, right? And we truncate this number up to some number. And let's say we will discuss this today, but the number n of equal to two-dimensional space is a representation of a qubit in quantum mechanics. Tinsley, do you have questions? If no, please, could you please mute yourself? Yeah, so let's go ahead. So usually we normalize these basis vectors to unit, right? And so the length of these vectors is 1. And in this way, we call these vectors or set of these vectors as a basis, as a basis. So, and when we introduce this basis, E sub I here, we can express any vector like V in this space as a linear combination of these basis vectors times the projections of the vector V on the basis, right? In other words, we have the vector V. This vector V can represent velocity, some fields like electric field. It can be a T function, as we will discuss today, little start discussing. And then we find the projections of this vector on the basis, which are these vectors EI. And this formula represents the vector V in our space in terms of basis vectors. The basis vectors can be you can, for example, rotate these basis vectors like in our space x, y, and z. I can say x and y lies in some plane, and then z goes up, but nothing holds me against of rotating this coordinate space arbitrary. And when I do so, I change my basis, and of course the projections of my vector will also change accordingly, but the vector itself will not change, of course, because vector can represent some physical object like velocities, and the velocity itself doesn't depend on how I choose my basis, right? But the components of the vectors, like components of velocity, for example, of course change. I change the basis, the components also change, but the velocity itself, the vector, is a physical object. For example, like a velocity doesn't change. So I introduced the basis. I found the components of my vector, and you can put actually this formula in a frame, because this is the, I guess, main formula like in linear algebra, and very important for us, because we will the similar way we will represent the state vector in our Hilbert space in a while. The vectors of a basis, this E sub I, are also vectors, right? And I can also represent them in our space. And the way I do so, I can write simply the string of numbers. It can be a column or a string. In this case, I wrote this as a string of numbers, and the string or column of numbers represent a vector, and each entity is the component of the vector. And for example, this basis vector E sub 1 can be represented by a string 1, and then all the other entities are zeros. For the second vector, it is 0, 1, and 0, 0 up to the mth element, and all the way down to the last one, e sub n. It is a string of zeros and n in the nth component of the vector. Very good. Then we introduce the three types of products of the vectors. The first one is the dot product, also known as inner product. The inner product is basically a scalar product of two vectors, and to calculate this product, I simply take the sum of the products of each components of the vectors. For two vectors a and b, these components a1, a2, etc., b1, b2, etc. The dot product is the combination like this: a1, b1 plus a2, b2 plus etc. up to a n, bn. And again, this n can be potentially infinity. And in particular case, when I find this the square of a vector, right, the product of a vector by itself, it will give me the squares of each component of the vector, which is basically the Pythagoras theorem. The second operation, the second product is cross product. Cross product is denoted by this cross here, or comma in the rectangular parentheses. And the way how we calculate the cross product is a determinant of three strings. The first one is the string of basis vectors, right? The second string is the row of components of the first vector, and the third is the set of components of the second vector. And determinant. You probably aware how to calculate. You probably know how to calculate the determinant. If not, we already discussed that last time, and I will briefly remind you today. And the third product is tensor product, denoted by the sign here is a cross in a small circle, and as a result of a tensor product, we get a tensor, or represented in the form of a matrix, like shown here. Say I have two vectors, a and b, with components a1, a2, etc., an, and vector b with components b1, b2, etc., bn. And then this tensor product gives me the matrix presented here, and this is in fact a tensor. And its components are equal simply to the products of basically all the combination of the components of the vectors. For example, the first string here consists of the product of the first component of the first vector multiplied by first component, second component, third component, up to the nth component of the second vector, etc. All combination of these components in the right order. Then we discuss this example. As an example, we took the Euclidean space. This is our three-dimensional physical space. We say that in our space we introduce this coordinate system, Cartesian coordinate system x, y, and z. These coordinate axes are orthogonal, the number of linearly independent vectors equals to 3. And then the unit vectors, the basis, we introduce in this space I, j, k, for example, and they are orthogonal. And then any vector, like vector A here, can be represented by its projections in the all coordinate vectors x, y, and z. And then we discuss how to find the dot product, this cross product. Here is the formula for the determinant and tensor product. Well, then we introduced the complex numbers and complex vectors, because for our quantum applications, you probably know that in quantum all these projections will be complex numbers, so we have to work in the complex space. So we say that the complex number is a combination of two, real number and imaginary number. Imaginary number is taken by its product with the imaginary unit, which is the square root from -1, so that the square of imaginary unit is -1. The formulas for finding the real part and imaginary part of any complex number. Then we introduce this exponential representation of any complex number. Any complex number is defined by its length, basically the amplitude rho here, and its phase p. And this this exponential representation is very useful for finding, any combinations of these complex numbers, like the product of two, taking the absolute value of complex number. I remind you that the operation of taking the real part of complex number consists in taking a product of the number with its complex conjugated version. And the complex conjugation means changing the sign of the imaginary unit. Right. And so we can introducing these complex numbers, we can consider any vector, like vector z. Again, it will be a string or a column of components of the vector z1, z2, up to zn. But now these components are complex numbers. And then we just started discussing the matrices in a vector space. So a matrix is a combination like this, right? This is a mathematical object. We denote the components of the matrix of a matrix by these indices I, j, and the I correspond to the row of a matrix. So when I is equal to 1, it is first row, 2 is the second row, etc. And the second index j is the column, the first column, second column, etc. So the determinant of a matrix is simply a sum of the matrix minors multiplied by this combination minus 1 to the power of I plus j. So when I plus j is even, then minus 1 to this power becomes 1, and you take the minor with the sign plus. Otherwise, when this I plus j, when the sum of the indices is odd, then minus 1 to this power becomes minus 1, right? And you take the minor with the minus there. And then you take the sum of, over all the elements in a row or a column. And in your homework, by the way, you've got several problems, and a couple of them are to find the determinant of a matrix, and I will say a few words about the homework today later on, and also I will give you, I will comment on the last maybe 3 problems there. I will comment on that. So the second operation with the matrix is the taking of its transpose, right? To find the transpose of a matrix. In order to find the transpose of a matrix, it's sufficient to change the columns by rows and vice versa, or simply meaning, or in other words, this operation corresponds to a rotation of a matrix by angle 180 degrees, right, around its main axis. Main axis is the axis with components C11, C22, C33, up to Cnn for a quadratic matrix. Very simple. And we denote this operation by small t here, or a tilde over the matrix. And in the language of indexes, this operation corresponds to exchange of the indexes here. It was ij, you replace ji, and that means that you replace the columns by rows and vice versa. The third operation is also simple. It's taking complex conjugation. Complex conjugated matrix is denoted by this star sign here, and it simply means that you take the complex conjugated of all the components. Dipansu, do you have any question?
No, Professor.
Yeah, so then please mute yourself. The fourth operation is the Hermitian conjugation. Hermitian conjugation is something a little bit more sophisticated, and this is what we really need to be to talk about quantum. Hermitian conjugation. So Hermitian conjugation is denoted by this dagger sign, or like little plus or dagger, and it consists in taking the complex conjugation of all the components of a matrix, right? And the transposition of the matrix, taking the transpose of the matrix. So you replace columns by rows, and then take the complex conjugated complex conjugation of all the matrix components. Well, and then we introduce the concept of a Hermitian matrix. Hermitian matrix, right? So what is a Hermitian matrix? Hermitian matrix is a matrix that doesn't change after taking the Hermitian conjugation. So you have a matrix like some matrix C, and then you take the complex conjugation, then make a transposed matrix, and you get, of course, another matrix in general case, but some sort of matrices they don't change after these two operations. This is very specific type of matrices. Not any matrices are like this. And these matrices are called Hermitian matrices. Hermitian matrix, very important. So I can tell you now why it's so important. It's important because we will see this today. The eigenvalues of a Hermitian matrix are real numbers, and for this reason, all quantities in quantum mechanics and quantum physics are described by Hermitian matrices. Like any physical quantity that can be observed in reality, because what you observe in reality are real numbers. The coordinate cannot be a complex number. The velocity cannot be a complex number. The energy, well, energy can be a complex number, but energy of isolated system, like energy of atom, for example, like a hydrogen atom or any kinds of atom, the energy levels are always real numbers, not complex. That's why all quantities in quantum mechanics are described by Hermitian matrices. And then we took this example, right? This matrix Cij, these components 1 and 2 at the main diagonal, and off diagonal elements are 1 plus I times 2 and 1 minus I times 2. So as you can see, the difference is the sign before this imaginary number, imaginary unit. So then what we did, we took the transpose operation of this matrix and you exchange the off diagonal components of the matrix, and the result is here, right? And then we took the complex conjugation version of this matrix and we replaced the sign here and here before the imaginary number, and we got this matrix here, which is exactly equal to our initial matrix. This means that this matrix here is complex, the Hermitian. The matrix is Hermitian, right? So even though the matrix is, it has the complex valued components here and here, and the structure might be somewhat complicated, but in fact, the matrix is Hermitian and its eigenvalues are real values. So this is where we stopped last time, and let's continue this introduction to linear algebra. So first of all, let's write this fact down, that let's say that this is the main properties of Hermitian matrix of a Hermitian matrix. So by the way, do you have any questions regarding this part? Okay. If no, then the first property of a Hermitian matrix is that eigenvalues are real. Eigenvalues are real. And let's sign this because this is very important. Eigenvalues, and the second one is that eigenvectors. Eigenvectors of a Hermitian matrix represents a basis. Eigenvectors of a Hermitian matrix represents a basis. What it means? What it means? It simply means that eigenvectors of a Hermitian matrix are orthogonal, right? And the number of these vectors equals to the order of the matrix. Like if the matrix is two-dimensional, it gets 2 columns and 2 rows, 4 components in total, and the matrix 2 by 2 gets 2 eigenvalues and 2 eigenvectors. And eigenvalues of such a matrix are real valued, and eigenvectors are orthogonal. Very good. So another important point here for our discussion is that a matrix can be thought as an operator of linear transformation. Let's write this down. A matrix can be thought as an operator. As an operator of linear transformation. Yeah, so this is always true, that a matrix, any matrix actually can be thought as an operator. This is new word here, operator. What is an operator? Usually we denote an operator like some capital letter with a part on top, like this. So this is operator. And what an operator does? An operator basically acts on a vector. Let's say a vector L or a vector V. And the result of this action, of this operator on a vector, gives me another vector, vector U. Right? For example, I initially have a vector V like this. I can represent the vector as a line with as a row, right? Arrow. And then this operator L acts on this vector and, for example, rotates the vector to another direction and changes its line, its length, like this, for example. And this would be my new vector U. So every operator changes vectors. This is in the operator notation, and I can write the same in the component notation, like this. So it will be the components of my new vector equal to the sum of the components of the matrix L I J, right? So and I multiply them by the components of my initial vector V J. So you see that this index I, this is the result, right? These components of UI, of components U, UIs are the components of the new vector, and this is the component that isn't changed. So it's here. I don't sum over component of over the components I. So my summation is over components J. And because they are they are here, right? So this J here and J here. So double J, the summation runs over the components J, and the result gets components with index I. And I remind you that the first, let me change the color. So in this matrix IJ, the first one, this I, represents what? It represents the rows, strings, and the second one represents the columns. Very well. So this formula here is simply matrix form of this formula of the operator representation, matrix and operator representation. And in some sense, you can say that matrix and operator representations are identical or equal, meaning that I can work either in the operator representation or in the matrix representation. That's like up to my up to my choice. Let's demonstrate that. So let's return to this operator representation. So my U is equal to operator L times, it's not times actually, it is action of operator on a vector V, right? So I can multiply this by the basis vector. I remind you that we are in a vector space. We set the basis, and the basis vector of this space is vector E with the VI. So this is one of the basis vectors in my linear space. So what I get from here? I get the product of vector U times EI. You see, this is the dot product or inner product of two vectors now. And what's equal? This is equal to the projection of vector U on the vector E sub I, right? So this is simply the projection or component of my vector U I. This is the result of the action on the left side of left hand side, and on the right side I get what? I simply get the following: E sub I vector, then my operator L, and vector V, right? You see that I multiply this vector here and vector here. Very good. So now I can represent my vector V as what? As the sum. Basically, I'm using this formula in the very beginning, right? This one, the representation of a vector as the sum of its projection on the basis vectors. Right. So I write V is the sum of components V times, or let's denote it by J. So J here, and the sum over J. And I plug in this formula here. So what I get? I get the following. So my UI is equal to the sum over J, then EI. This is free index because it doesn't change when I run my sum over J, right? And then this operator L. Then I put EJ here from this expression, right? And times what? Times Vj. So now I can look at this formula and notice that I have this combination here. So this combination here, I vector, L operator, EJ vector, I can simply denote this expression by Lij, right? And when I introduce this matrix Lij this way, so this is basically the definition of the matrix components that correspond to operator L. I can rewrite this formula this way. Ui is equal to sum over j, Lij, Vj. This is the formula we started with, this one. This basically means that the operator representation and the matrix representation are basically equivalent. Very good. So now let's consider an example. Let's consider an example. So let's take the let's take the matrix from this previous example. Let's put this star here. So this example we discussed last time. This matrix Cij presented here. So let's take the same matrix. So it was 1 here, 1 plus I times 2 here, 1 minus I times 2, and so. Yeah, and we already figured out that this matrix is coincide with its Hermitian conjugated, right? Which is the complex conjugation and transposition of the matrix. Let's say a few words about the eigenvectors and eigenvalues. Eigenvectors and eigenvalues. So, eigenvectors and so you are supposed to be supposed to know these things. I just remind you this results from linear algebra. So so if I have an operator like any operator C, for this operator I can write this expression C times some vector E equal it, and it's equal to alpha times the same vector E. So when this realized, then this alpha is the eigenvalue, and this vector E is the eigenvector. What it means? It means that for a particular matrix C in my linear space, I can find a vector E called eigenvector that is being changed by operator C just I mean, the result of the action of the operator C on this vector is equal to just multiplication of this vector by the value alpha. This value can be, of course, complex, and this value alpha, this quantity, is called eigenvalue of the operator, or eigenvalue of a matrix. I remind you that operator and matrix representation are equivalent. So how do we find the eigenvalues and eigenvectors? So let's rewrite this expression here in the matrix form. It will be some. So now let's use the Einstein summation rule that says that for any expression, if I have two indexes, summation indexes like here jj, right, jj, then I can omit this summation sign and simply write Lij times Vj, and I just remember that this is actually the sum of elements. This saves our space and makes everything looks good. So we can represent this formula for eigenstates and eigenvalues in the matrix form. So it is C ij, then the vector ej, this is a vector, is equal to alpha e I vector, right? So you see that there is a summation over component j. So after summation, it's gone, and I left with one component. I mean, the components denoted by I here. That's why we have this component I. This is called the component balance, and it must be like matched on the right and left side of any expression. The components must be named in the same, let's say, properly. Very good. So now we can move this right hand side to right hand side to the left part. It gives us what? Cij e vector j minus alpha ei vector equals to 0. Right. So here I have this I with index j, but here it comes with index I, so I need to change that. How I do so? I last week we introduced this this object delta. This is Kronecker delta symbol with two components I and j, and this is basically a matrix, like unitary or identity matrix: 1 0 0 blah blah, 0 1 0 blah blah, 0 0 1 blah blah blah, etc. So this is the quadratic matrix with units at the main diagonal and zeros otherwise. And having this matrix, I can rewrite this I e I as a product of this delta ij times ej. All right, because this delta ij times E with component j, it runs, I mean, this is a sum, again, this summation over this these indexes j here, and only those deltas that have the same I and j will survive eventually, right? So you will see that this always holds. You can write your vectors in this way. So let's rewrite. Let's use this here and rewrite this Cij times Ej minus alpha delta Ij Ej vector equals to 0. So I can rewrite this by taking the Eij out from the parentheses. So I get Cij and then minus alpha delta Eij parentheses times E j equals to 0. So you see, this is the linear equation. Actually the system of linear equations, and this system of linear equations has a solution only when the determinant of this expression here is equal to 0. So determinant of this expression must be equal to 0. Only in this case, the system has the not trivial solutions, let's say. So I write that determinant of this Cij minus alpha delta ij equals to 0. This is called Kramer's rule. So as far as I remember, it's Kramer's rule. Kramer's rule. So, and this Kramer's rule allows us to write down the characteristic equation of our matrix. Characteristic equation. So how it works in our case for our matrix above, for this one, for this matrix, right? I simply have to write the same matrix according to this equation. So this matrix here, but for the diagonal components, I have to subtract alpha. And this alpha will be the eigenvalue of my matrix, right? So I write for our example, right? For our example matrix, I write the following. So I have to write this determinant of matrix 1 minus alpha. Then off diagonal components don't change because this delta here is equal to 0 for off diagonal elements, right? And this alpha turns to 0. So for off diagonal elements, I will get 1 plus 2i, here 1 minus 2i, and another 2. This is 2, right? No, this is alpha. Sorry, this is alpha. This is this is 2 minus alpha. Sorry, my alpha and 2 look very similar. So I have to find this determinant. So fortunately, this is matrix 2 by 2, and it's very very easy to find. What I do, I take the product of the diagonal elements minus the product of diagonal elements. What I get? I get 1 minus alpha times 2 minus alpha minus 1 plus 2i and 1 minus 2i, right? Equals to. So now looks at this part here. 1 plus 2i and 1 minus 2i. These are two complex. This is the product of the complex number by its complex complex conjugation, right? So what it is? It is equal to in this case it will be 1 squared times let me see. So let's take it. 1 plus 2i times 1 minus 2i. So it is 1 squared plus 2 squared, which is 4, equals to 5. Yeah, so in this case, the result is equal to 5, right? And this guy here, 1 minus alpha and 2 minus alpha. What I get? I get 2, then minus alpha, then minus 2 alpha plus alpha squared minus 5 is equal to 0 by by our definition of the Cramer's rule. So this 2 and minus 5, right? I can simplify this and write alpha squared in the first place, alpha squared. Then I see minus 3 alpha, and then minus 3 is equal to 0. And you see the the solutions of this quadratic equation is was denoted by 1 and 2. Right, so it will be 3 plus minus square root from 21 over 2. Right. So so first of all, I noticed that these two, I've got two values because my matrix is 2 by 2, so I expect to get two eigen values for my matrix. And even though my matrix is has the complex valued components, the eigenvalues are real values. So this is real values. And this is a big deal for quantum mechanics. This is a big deal, and this is only for Hermitian matrices. Very good. And then how you find the so when you found the eigenvalues, the task of finding eigenvectors is relatively easy. You just for each of these eigenvalues, you put these values to this expression here, and this will give you the system of two linear equations for two unknown elements. You can solve that and find the eigenvectors. This is, by the way, the problem for your, I mean, in your homework. you have this assignment to find the eigenvalues and eigenvectors of a matrix there, or a couple of matrices. So you will get a chance to practice with that. And the important point here is that for this real valued eigenvalues, the eigenvectors, the corresponding eigenvectors, there will be two eigenvectors. These eigenvectors will be they will be orthogonal. They will be orthogonal. And you can do yourself and check that. The only the only point here to to maybe comment is that the way us for the complex number, when we want to take when we want to get the real value, we take the product, not the number by itself, but taking the complex conjugated. The second part must be complex conjugated to get the real value. And for the complex vector, like z, right? This is it has components like column z1, z2, etc., zn. These components are complex valued. All of them are complex numbers. And when I take the product z by z, right? So this is the let's say when I solve this for the length of the vector squared, modulus of z squared is the length, right? I have to write something like z times z, right? But in order to make this number real valued, I have to take the complex conjugation, either first or the second, it doesn't matter. And what is more important is that when I write these vectors in the column or string form like this, in order to find the inner product, the first vector here must be a column, right? But the second one must be a row, like this. No, actually, I'm wrong. Sorry. So the first one must be a row, but the second one must be a column, like this, because I take the product of two vectors columns by the rows by columns, right? So this way, taking the product this way, I will get what? I will get z1, no, in this case, z times z conjugated, say 1 plus z2 conjugated, etc., all the way up to zn complex conjugate. So my point is that when you take the product of two complex vectors, you have to remember that you take the complex conjugated of one of them. And this is always true, always correct. But when you represent your vector in a column form, you take the transposed first, right? You change your column into a row elements shown here by these two lines. This is column, this is row, then complex conjugated, right? And then times the column of the vector. So this is the comment on the taking product of two complex vectors. Do you have any questions? Very good. So what else I can do with matrices? I can take the matrix product, right? So this is another type of product that we didn't discuss yet. So matrix product. So the matrix product of two matrix, let's say A matrix and B, is what? It's simply another matrix, right? The product of two matrices is the another matrix with the number of rows and with the number of rows of the first one and the number of columns of the second one. So let's write it this way. So the first matrix A has rows times n columns, and we take the product. The second one, the number of columns must be equal to the number of rows must be equal to the number of columns of the first one. So this is the matrix B. K. So the result will be another matrix MK. In the component representation, I can write it this way. So this matrix A with components I, J. Then goes matrix B. And now I have to run these matrix components J here. So you see I, A, I, J times B, J. Let's actually use the same notation. So matrix A with components A, M, N here. I use the same letters times B with indices N, K, and the result will be another matrix C with remaining components. So this component N here and here is a summation over this component N, right? And the result is matrix C with components M, K. Component N, K. So this is kind of a rule. When you write your matrix product, the first matrix comes with has the components Mn, and then the second matrix you run your when you write the matrix product, you sum up all the components with the second index of the first matrix and the first index of the second matrix. Here, like for example, writing something like B and K times A M N, something like that, wouldn't be correct. In general case, in general, it's not correct, because here your first index and the second and the first part, the first place, and the second and the second place. So it's not correct to write this down like this. Your matrix product always second index by first index, second by first. Properties of a matrix product. Of matrix product. So first of all, if you have three matrices, like A, B, and C, and you take the product of three, right? How you can solve this? You can, for example, write the product of B, C, and then multiply by A, or you can take the product of A, B, and then find the product with matrix C. So basically, what is important is the order of matrices A, B, C, but the order of matrix product doesn't change the result. Doesn't change the result. And this is the first one. And the second property is that is about basically the transposition. So if you have a product of matrix A times matrix B, right, and you make the transposition, it's actually equal to the B transpose times A transpose. So you see that you write the matrices in the reverse order, A times B, now it's B times A, and the transpose of the corresponding matrices. And as a result of this, for example, when you take the Hermitian conjugation, A times B, Hermitian conjugation, again, the result will be B conjugated times A conjugated. And let's prove this fact. Let's prove this property because it's pretty important for the further analysis. So we have A matrix times B matrix Hermitian conjugate, the dagger symbol. What it is? It is actually the summation, right, over let's say, so my first matrix A, I can write any indexes. I mean, I can note these indexes by any letters. Let's write I, J, right? Then the second matrix must start from, I mean, index. The first index of the second matrix must be J, because I take the matrix product of two. And the last index may be any letter, K. Summation runs over J, and I take the dagger here, the Hermitian conjugation. Right? So what does the what the Hermitian conjugation does? It simply exchanges the indices and makes the complex conjugation. So my A ij will be A complex conjugated ji, and the second one B bkj complex conjugated. Right, but we already said that this is something wrong here because the j must be at the second place here, and here j must be the first indices. So I have to exchange the position of this two. So I write it this way: summation j b kj complex conjugated times a j I complex conjugated. And so now now it's correct, and now you see that so this is basically the product of B complex conjugated, A complex conjugated, but look at the indices. So here in this matrix, indexes are kj, but initial matrix was with indices jk. So we transpose the matrix, right? So the result is B matrix complex conjugated and transposed, and A a complex conjugated transposed, and both of them are a Hermitian conjugation. So this is B dagger A dagger. This is the proof of this property above. A times the Hermitian conjugation of the product of two matrices is equal to Hermitian conjugations of the matrices taken in the reverse order. Very good. So now we introduce this matrix product, and let's introduce the inverse matrix now. Inverse matrix. In your homework, you also have an assignment, the problem to find the inverse matrix. So it is always important to know how to find the inverse matrix. So what is an inverse matrix? Let's say we have a matrix A, and we say that this matrix A has the inverse matrix denoted by A minus 1 here. It's not power, it is the notation for the inverse matrix. So that the product of matrix A with the matrix product of matrix A with the inverse matrix gives me what? Gives me identity matrix. So we can write this identity matrix I. Sometimes we write this identity matrix. Let's write this way. Sometimes you also can write this like 1 with hat, like this a matrix, the identity matrix, and also in matrix form, this identity matrix, we also use this symbol, Krasnok symbol, right? This delta ij. So the identity matrix is simply 1 0 0 0 etc. 0 1 0 etc. 0 0 1 etc. and all the way like down for so basically units at the main diagonal and the zeros of diagonal components. And this is very easy to understand for the vector, like right? Like, let's say a vector. A vector is also a matrix, but just one column or one row. So the vector C, let's say vector C, I have vector C, and then I write the same this way. Vector C times a vector C minus 1. So this is the inverse vector. And I imply that this result must be equal to 1, basically 1. So this is scalar product, so the result is scalar, so the result is 1. So how I do so? So I can see from here that my inverse vector, my C minus 1, it's simply equal to, simply equals to what? The vector C itself, complex conjugation, over the length of the vector C squared. Why? Because let's take the product of two. I have this vector C, right, times E vector complex conjugated I mean, here I assume that my vector can be a complex vector over C squared, right? But C vector by C complex conjugated is simply equals to modulus C squared. So I get modulus C squared here, modulus C squared here. This gives me 1. So the reverse vector, the inverse vector is the vector itself, complex conjugated if the vector is complex, divided by its value. This is how it works for vectors. But what about matrix? For a matrix, the formula is a little bit trickier, and let's write it down here. So suppose you have a matrix A, some matrix A with components A11, A12, A13, etc. Then A21, A22, A23, etc. and etc. So this is the matrix you have. So the the formula for the inverse matrix A will be 1 over determinant of the initial matrix times another matrix, right? It's inversion matrix, so it's supposed to be a matrix of this construction. Minus 1 to the power of I plus j. We already saw this when we discussed the determinant. Times the minors, the matrix of minors, ij of the transposed matrix A. Transposed matrix A. So now it it looks very maybe unclear, but let's consider example. Let's consider our example. This matrix C 1 plus I2 1 minus I2 and 2 here, right? So this is our matrix that we we already know that this matrix is Hermitian. This matrix has the real valued eigenvalues. We already know how to find them. And let's now find the the inverse matrix. Inverse matrix. How we do so? So the procedure is as follows. So first we find determinant of this matrix. Determinant of this matrix. We already did that, and in our case, the determinant of our matrix C is equal to minus 3. See the previous previous example, minus 3. So the second step is to find the transpose of the initial matrix. What it is? It is 1 here. So basically, the diagonal elements don't change, and the off diagonal is replaced by 1 minus I2, 1 plus I2. All right. So this is our transpose matrix. And then I need to third. I have to write this matrix of these elements, minus 1 to the power of I plus j, and matrix of minors, ij of the transposed matrix C. So let's do that. So let's take the first element. The first element 1, C11. For this element C11, I is equal to 1, j is equal to 1. 1 plus 1 gives me 2, even number. minus 1 to the power of 2 equals to 1. So I have this plus here, and then I need to write the minor for this element 1, 1. How I do so? I remind you that the finding of the minor is simply taking this element and removing the corresponding column and the corresponding row. What I get this element 2 here. So this is my minor of my matrix. So I write plus 2. The same way, for the second component. My second component is C12. 1, 2 gives me 3. Minus 1 to the power of 3 is minus 1. So I put minus for the second element. And now for this element, I remove this row and this column, and I get this element here, right? So this is my minor of this matrix of the corresponding element. So this is my 1 plus 2i, and etc. So now you can see that this, for example, this third element here, which is 2, 1, also gives you minus here, and then this element here, I2, and finally 1. So this is the matrix. And finally, the fourth step is to basically to write the result. The inverse matrix C minus 1 inverse matrix is equal to 1 over determinant of initial matrix, which is minus 3. So it is minus 1 over 3 times this matrix of minors. 2 minus 1 plus 2i minus 1 minus 2i and 1. Okay, so this is the answer. And now you can check that the product of initial matrix C times this inverse matrix that we found gives you basically not 1, it will be identity matrix. Let's denote it by E. So in your homework is denoted by E. In your homework, as far as I remember, I mean, anyway, so this E denotes the identity matrix. Do you have any questions about this part? Okay. So what's the meaning of this inverse matrix? So we already saw that a matrix corresponds to some linear transformation in our linear space, right? I have a vector. I just recall you that if I have a vector, I multiply this vector by a matrix or operator. It is the same thing here. This will give me another vector v. But now, what's the meaning of the inverse vector? let's multiply let's multiply this by inverse matrix on the left side. It means that I put this a to the power of minus 1 here, then vector a, and then the matrix A, then vector U is equal to A minus 1 vector V. Right. I know that this operation, because of the properties of matrix products, right, equals to this one. And now this one, a to the power of, I mean, the inverse matrix times the matrix itself gives me what? Gives me the identity matrix. And the identity matrix times any vector gives me what? Gives me the vector itself. So therefore, this is equal to the vector u, the initial vector, right, equals to a to the power of minus, so it's not a power, it's inverse matrix times the vector v. Let's write this formula too. So our initial operation by that corresponds to matrix A does what? We had initially we had this vector u, then we apply this vector, matrix A, and this result is given us another vector v in our vector space. So the matrix A is an operation that takes one vector and creates another one. Basically, it is a rotation and scaling, right? But for the matrix, for the inverse matrix, we get kind of opposite. So the inverse matrix represents the opposite transformation. The reverse matrix represents opposite transformation. So yeah, it's very easy to grasp, right? If a matrix gives some kind of transformation, then the inverse matrix basically gives the opposite transformation. So application of two returns your system to initial state. And now let's introduce the concept of unitary matrix. So this is like extremely important, and I guess one of the main points of like entire story of quantum computing, etc., quantum mechanics. Unitary matrix. Unitary matrix. This is very important. I mean, matrix and also operator, right? So matrix operator. Unitary matrix, unitary operator. So we already discussed this concept of Hermitian matrix. Hermitian matrix, we said it is a matrix that has real valued eigenvalues. And we said that this is important for quantum mechanics because in quantum mechanics, any any quantities that we measure in a lab, right, they all have real values. So any quantity in quantum mechanics is represented by, we will see that maybe next time, but now let's say it this way: any quantity in quantum mechanics is represented by Hermitian matrix. And Hermitian matrix is just very like narrow class of matrices, basically those that coincide with with its transposed and complex conjugate. So unitary matrix is another sort of matrices. It's also like very specific, and it what it does basically, why it's so important. It's important because unitary matrix transforms vectors leaving the scalar products, the inner, let's say inner product of the vectors unchanged. So unitary matrix also does some sort of linear transformation, as well as any matrix. But unitary matrix does a very particular class of transformations that leave unchanged the scalar product of vectors. Well, let's demonstrate it this way. So let's suppose we have a matrix A prime, or not matrix, a vector A prime, and another vector B prime. And you remember that when we take the product of two, I mean, we suppose that they can be complex, the complex valued. So we have to take the complex conjugation of the second one. Complex conjugation of the second one. We can express this as a sum, right, of corresponding components of vector A, vector B, complex conjugate. Sum runs over this index I here. So vector A, for example, prime, is equal to let's assume that vector A prime is the result of the action of some matrix U ij on a vector A, J, right? So I have this vector Aj. I take a matrix Y, and the result of this action of matrix I, or operator Y, Y on a vector A gives me another vector A prime, and the sum runs over J here. And the same for the vector B prime. I, it is equal to sum J, the same operation U I J B J. So now let's plug in these two transformations into the formula for the scalar product, right? So what we got? A prime vector B prime vector complex conjugated is equal to the sum. It's actually double sum over J and over, let me see. So let's do step by step. It's actually triple sum. So anyway, sum here, it will be sum over J U I J A J, right, for the vector I prime, A prime. Then for the vector B, let's denote this summation index by k. So it will be u I k b k and complex conjugate. Complex conjugate here and here. Let me replace this guy here. Okay. Yeah, and summation over I here as well. Let's denote by single summation sign all these three, right? To make it short and accurate. So now I can write this way. So matrix U I J. I simply rewrite this string here. U I J, then A J, then U K B K complex conjugate. Oops, sorry. This. Very good. So now, now let's exchange the positions of these two. So I have these two vector product or products of operator U and A and B vectors. Let's put the first one, the first place, and the first one, the second place, exchange the position, and rewrite this as follows. So it will be sum of U complex conjugated I k, then B k complex conjugated, then U I j I A j. Okay. So now let's look at this operator, this matrix U I k. I can put this. I mean, I can exchange the position of B and U by taking the transpose of the matrix U I k, right? So I can simply rewrite this by the following: bk complex conjugated, this is the vector here, and then times U k j complex conjugated transposed. So when I take the transposed, this k and j change the the order, and let me see. So it's not B, it's not J, it's I, right? This is I. And then this matrix U I J and vector A J. Okay. And sum over all the components over K, I, and J. Very good. So now what we have? We have the components of the vector B, complex conjugated here. Then components. Oh, yes.
Can you explain this step again? This UIK changing to UKI with the transpose?
Yes, you change the order of indexes, right? So you had this UIK. You can make the transposed matrix, so it will be UKJ, KI.
Okay, okay. Oh yes.
So basically, yeah, this exactly equal to this guy. So I didn't change anything, but the only point to like bear in mind is that the second index in the matrix, when you take the product of two matrices like A and B, right? You take the sum over the second index in the matrix, in the first matrix, and then the first index in the second matrix. So here J is second index, here the index is the first one. And the same for the vectors. When you take the product of matrix and let's say a vector, then your matrix gets two indices, I, J, and then this vector must have the index J. And the rule is as follows. The second, when you write the expression like this, the summation index must be the second in the matrix, right? So when you when you transpose the matrix, like we've done here, you have to replace the order of the vector components and the matrix components to make this rule consistent. So you have this k here and k here. So now it's on the first place, this index k on the first place. That's why I write the component of the vector first and then the matrix to make this rule consistent. So this is basically a rewriting of the same thing, just taking transposed of the matrix. But this allows me to notice the following. If I have here the product of two matrices, right? This matrix U. So let me write it down here. So I have this matrix U Ki and matrix Yij. So this is basically the product of matrix U by matrix U by itself transposed, right? And complex conjugated. So the transposed matrix and complex conjugation is what? Is the Hermitian matrix. And I noticed that if this product of the matrix times the Hermitian conjugated matrix is equal to identity matrix, when it's equal to identity matrix or unitary matrix, then the initial scalar product A times B will be simply equal to again the product of B times A, which is the same. So from here we conclude that if the Hermitian conjugated matrix, first of all, so let's write this one here, U times U dagger, right? Hermitian conjugated dagger is equal to E. And now let's multiply by inverse matrix, both sides on the left. The product of any matrix with the unitary matrix gives the matrix itself, but here I get minus the inverse matrix times the matrix itself times the Hermitian matrix equals to the product of the inverse matrix times unitary matrix. So now I see that this guy gives me the identity matrix, and from here I conclude that for unitary matrices this is true. The Hermitian matrix coincides with its inverse matrix, and this is very, very important. This is very important. So basically, this is definition of a unitary matrix. Basically says that if the Hermitian conjugated matrix, if the Hermitian conjugated matrix coincide with its inverse matrix, then the matrix is unitary. And another sentence that probably important to understand: the unitary matrix and the corresponding transformation, right? We say that any matrix corresponds to some sort of transformation or a operator. So unitary matrix and the corresponding operator. Don't change. Doesn't change. Oh, don't change. The dot product, the inner product. And as a result, of course, and the length of the vector, right? Because the length of a vector can be written as the product of a vector by itself. So the unitary transformation, unitary matrix, doesn't change the inner product, and as a result of that, doesn't change the the length of a vector. Yeah, so any arbitrary matrix corresponds to some linear transformation of a vector, and this transformation consists in rotation of a vector and changing its length, right? It's either scaling down or scaling up. And the unitary matrix corresponds to a particular class of these transformations that correspond to only rotations in some space, in vector space, without change of a length of a vector. And on top of that, without change of the scalar product of two vectors. And why it's so important? It's important because any operation in quantum computer, let me say these words now, and we will talk about that in what follows. Any operation in quantum, let's say in quantum mechanics in general, and in particularly in quantum computing, is described by unitary matrix. Any operation in quantum computer, in quantum information, in quantum mechanics, whatever, is described by unitary matrix. The easy way to grasp this idea is to say that is to recall that the state of a quantum system is described by state vector, right? This psi vector, and this vector in some space we will discuss. We will see that the space is Hermitian space, and any operation with a quantum system is described by basically a rotation of this vector state. And this rotation is represented by the unitary matrix. So, and you will see that any gates, let's say any gates in a quantum computer is described by a particular unitary matrix. So basically, you have a set of unitary matrices, and those unitary matrices correspond to different quantum gates in your quantum circuit. Right, but for now, let's consider an example in our Euclidean space. Example. Rotation was denoted by rotation in the Euclidean space. In Euclidean space. And for simplicity, let's consider two-dimensional space, 2D. Right. So we know that in two-dimensional space, like plane, like a surface, right? This is our two-dimensional geometry. What we do, we introduce this axis y and axis x and y. Since when we introduce this x and y axis, we can describe a vector A by its projections on the corresponding on this axis, right? So I just want to repeat these words. In two-dimensional space, the number of linearly independent vectors is 2. We introduce these vectors as x and y, right? And by the way, the basis will be I vector and j vector. Don't mix them up with the components I and j. Components, just components, you can name them by any letter. These basis vectors I and j is a vector. The vector gets a number of components, etc. So it's very different. Don't confuse them with the indices. So this is the basis, vectors I and j. In our two-dimensional space, we have just two linearly independent vectors. And when we have some vector A, this vector exists in a space, and it can be, for example, some sort of a physical quantity like velocity, like pressure, electric field, current, whatever. It exists in reality and doesn't depend on the way how we introduce our vector, our basis, right? But when we introduce this basis, we can describe this vector by its projections on the corresponding vectors. And in this coordinate system, the corresponding components of the vectors are ax and ay. So this is our vector A in this coordinate system, right? And let's now rotate the coordinate system to another one by some angle phi. Well, this is the new coordinate system. Let's denote it by y prime, the x prime, and you see that this coordinate system is rotated by angle phi. Angle phi here and here. All right. And the question now is how to represent the components of the of the vector A in the new coordinate system through the components of the vector in the initial coordinate system. And the solution is given by the so-called rotation matrix. So let's write this way. A prime is the same basically vector, but the components of the vector will be different in the new primed coordinate system. So this transformation is represented by a matrix R in the operator form. I'm writing now in the operator form R times A. In the matrix form, this matrix R gives the components cosine phi, sine phi, minus sine phi, cosine phi. You can easily check that. So yeah, first of all, this matrix, and then times this initial vector ax, ay, right? So yeah, now we, by the way, can practice the matrix product, and from where you can see that this is actually the correct result. So how we do the matrix product? In this case, this matrix by a vector, which is the matrix but with 2 rows and 1 column. So we do this the row by column, right? So what we get? Oops. It will be a matrix, or it will be a vector with components cosine phi times ax, then plus sine phi times ay, right? And then the second component is minus sine phi ax plus cosine phi ay. So this is the result. This is basically the ax prime, and the second element is ay prime. So these are new components of the same vector, but in the rotated coordinate system. For the matrix itself, this matrix R is what? it is cosine phi, sine phi minus sine phi, cosine phi. So this is the matrix R. What is the inverse matrix? So we can do this procedure, taking the determinants, then find this matrix of minors, etc. But we already say that the inverse matrix corresponds to the inverse transformation, right? So we can immediately write this inverse matrix by the rotation in the inverse direction. So we basically changed phi by minus phi. And cosine phi is the even function, so it doesn't change the sign. Cosine phi here, cosine phi here. And sine is odd function, and it changes the sign. So it gets minus here, sine phi, and minus sine phi, and here, sine phi here. So this is the inverse matrix. And this matrix, of course, doesn't change the length of the vector, right? Because this is just rotation of the coordinate system. It doesn't change the vector itself. And of course, it doesn't change the scalar product of two vectors, right? It's very easy to see. And so the idea is that this matrix is probably unitary. This matrix R is a unitary matrix. And and let's actually check that. So we remember that the unitary matrix Hermitian conjugation, right? If the matrix is unitary, it must coincide with the inverse matrix. So let's check that this is actually correct. How we do so? Oh, we first we find the Hermitian conjugation matrix of the initial one R. To do that, we take the complex conjugation, but this sine and cosine functions are real. So the Hermitian, the complex conjugation doesn't change anything here. And then I remind you that the Hermitian conjugation, R dagger, is the same as the complex conjugation and and taking the operation on transfers. The complex conjugation doesn't change the thing, and the transposition of the matrix simply rotates this matrix around the main diagonal, which gives you the following: cosine phi minus sine phi, sine phi, cosine phi, right? Which is exactly the same as I mean, it's coincide with the inverse matrix that we just defined, this minus this inverse matrix R minus 1. So for this particular matrix, the Hermitian conjugation coincides with the inverse matrix. So the matrix R is unitary. Unitary, sorry. Yeah, so you see that the rotation matrix is a unitary matrix. In fact, one can say that any rotation matrix is actually unitary matrix, because what you do, you just rotate. You can rotate either the coordinate system, or you can describe the same process as the rotation of a vector without changing the coordinate space, coordinate system, this basis. So you either rotate vector, fixing the basis, or you keep the vector unchanged and you change the basis. You rotate the basis. The result is the same, and any operations like this is a unitary operation because it doesn't change the vector length and scalar product of two, inner product of two. So now let's introduce very important thing. Let's introduce so-called bra ket notation. It is also known as so-called Dirac notation. Dirac notation. After this great scientist, Paul-Marie Dirac. Very important concept, bra and ket notation. And why it's so important, you will see in a second. So we say that a vector, like vector, for example, x, can be represented by a set of numbers. We can write these numbers as a string of components, x1, x2, etc., xn. We can write the same as a column of the same, basically, components, the same components, right? And to make it more like unified, let's say, we can do the same using this bra and ket notation. So let's introduce this ket vector x put inside this funny parentheses. This vector vertical line and this angle parentheses. So this is called ket. Ket. And this ket is a vector ket or ket is again represented by its components, x1, x2, all the way down to xn. The column of components. So at this point, let's fix this notation. So the ket corresponds to a column, not a string, a column. There is another component, this another object that actually corresponds to a string. The response to a row is so-called bra vector. Let's denote it by this. So this is the bra, and it's simply equal to the transposition and the complex conjugation of ket. So I write y ket, and then I take the transposition and complex conjugation. So as you can see, it is transposition makes changing the column by its row, right? So I write y1, y2, etc., yn. So these components of the bra. But on top of that, I have to take the complex conjugation of every of each component to make it consistent with the previous discussion when we took the scalar product of two, and we saw that the result is real valued when it is the vector times the complex conjugated vector. Let's let's demonstrate it this way. So we have bra vector, and we take the inner product with another cat vector. At this point, you see that I mean, why this terminology here? This inner product now makes the word bracket, which brackets, right? So this bracket, this inner product, we never write it in this form. We for briefness, for simplicity, we write it in this way. So y, just one vertical short line, and then x. So this is the inner product of inner product of two vectors, and the first vector is the bra, which is the string of components y1 conjugated, y2 conjugated, etc., yn conjugated, right? So this is the string, and then the column x1 for the cat, x2, etc., xn. You see? So according to this is the product of two vectors or two matrices, you might say, and the result is simply y1 conjugated x1 plus y2 conjugated x2 plus etc. plus yn conjugated xn. That's xn. So simply inner product or dot product of two vectors. Again, this cat is a vector, and a dual vector of two cat is a bra, and the inner product of two vectors, the cat and bra, gives you the scalar, and on top of that, the scalar is real valued, because you take the complex conjugated times the component, then conjugated component times component, and take the sum. So this guy is real valued. And in particular case, the inner product of the vector itself, what it is? It is simply x1 conjugated x1 plus x2 conjugated x2 plus etc. plus xn conjugated xn, which is simply the modulus x squared, right? Basically the square of the length of the corresponding vector. So now, so today we said that the matrix or operator is the operation that creates another vector. Let's write this in the bracket notation now. So I have, let's say I have cat vector x, then I act my operator on this vector x, and in the result I get another cat vector y. All right. So now let's take the how to say this. Let's let's take the transposition and complex conjugation of this vector. All right. Transposition and complex conjugation gives me the bra vector. So it simply equals to y bra. On the other hand, it's equal to this operator L times X and this complex conjugation and transposition. It doesn't matter in which order you do your complex conjugation or inversion, because I mean they both commute. So, and from this rule, let me see, from the properties, from this property, right? You from this one here, the transposition of the product of two matrices is the product of two transposed matrices in the opposite order. So from here, using this rule, you can apply this transposition here and write the X transposed times L operator transposed and then complex conjugate. So now let's apply this operation of complex conjugation to both. This operation, of course, doesn't change the order, and we get this X transposed complex conjugation, then L operator transposed complex conjugation. So transpose and complex conjugation, in the case of operator, it is what? It is Hermitian operation of Hermitian conjugation. So this is L dagger, right? And on the other hand, this guy here is the Bra vector K, or by Bra vector X. So this is equals to Bra vector X. So the result is the Bra vector and operator complex conjugated. So it's pretty interesting. So for the ket vector, the result of the application of the operator is this one, right? When you apply your operator to a ket vector, you get another ket, and the operator acts from left to right, like usual writing. But now in the case of Bra, from this right here, in the case of Bra vector, you first write the vector, the Bra vector, and the operator on the right side. And the operator must be Hermitian conjugate. Next time we will practice a little all these things, because I know that there is a lot of kind of on one side, I mean, one hand, you supposed to have the course on linear algebra, and you're supposed to know this Hermitian conjugation, unitary matrices, etc. On the other hand, it is quite, I know it's quite like difficult to bear in mind all these concepts and things. And next time we will solve a number of problems to master the things. So this is application. So now the point is that for the Bra vectors, the operator acts from right to left. In the case of ket vectors, the operator acts from left to right. For bra vectors, it is opposite. So this is something that like you better remember. So now for this bra vector, which is x times L dagger, let's take the inner product of itself with the corresponding cat vector. So it's y times y cat, right? What I get? I get this x, then this operator Hermitian operator, Hermitian conjugated operator, and then for cat vector, of course, it is L times x vector, right? This one, this expression here. So it will be L operator times x. And again, so I require that the inner product of two vectors, cat and bra, is not changed after the application of this, after acting of this operator L, right? So this will be equal to the inner product of x only if the product of two operators L dagger L is equal to 1, or I mean unitary operator. And so it requires that the Hermitian conjugation of my operator is equal to inverse, operator inverse. So again, this is the fact that we already know, but now written in this bracket notation. But this is just the first. This is the inner product, right? This inner product. But you may ask, what about the outer product? Because
Alex, I have a question.
Yeah.
About this Brian ket notation. In the ket, we are applying the operator firstly, and then we are having that. So I'm not able to understand what is the use of, means from left to right and right to left. You told about this operator L. So how is that applicable? Means, is it applied later on in the processing, or how is it done?
So it is actually applied the way as it usually applied. Just operator acts on a vector. This expression here is just a way we represent things, the way how we mathematically write the things. But if I would have to calculate this, right, the operator and acts on the from right to left, I would simply take this operation as I would do in the normal case. Let's say let's write it here. So let's say my vector bra is some sort of a radius vector, for example, right? So this is a radius vector like this, and I apply my operator let's say it is a rotation operator, so it's just or not very representative. Let's say the operator is some sort of partial derivative dx, like this. So I wrote this way, but I just have to remember that now my partial derivative operator acts on the left. So if I compute this, I simply compute dr over dx. But the way I write this, like as a expression, I have to write it this way to be consistent with this part, with the inner product and outer product as well, that we're gonna discuss now. So this is just the way we write things, but when we do computations, right, we do the calculation like in a usual way, let's say.
Thank you.
All right. So now the second one, the outer product. Outer product. What is this? So the inner product is the product like this, right? The bra then goes cat, and the bra times cat gives me a scalar. But there is another product, outer product, which is the product of cat and bra. So this, let's say not x, let's say a. So this is a cat times bra cat. So again, for simplicity, we simply write this as follows. So it's a and then this cross b. So this is exactly the same thing. We don't write this two brackets, angle brackets here. And we know that a cat is a column, right? A1, A2, etc. And then the the bra vector is a string, B1, B2, etc. And when we take the product like bra and then cat, then we multiply them as a scalar product according to the usual matrix product rule. But now when we have this outer product A times B, this simply means that the cat is on the first place, A1, A2, etc., all the way up to AN. So this is the column, and then it multiplied by the string B1, B2, etc., Bn. And this is something new, right? Because this is, I mean, according to the matrix product rule, we have to take the elements from a row of the first matrix, then multiply by elements of the column. But now we have the column in first place and the row in the second one. So basically, this product gives me a matrix of elements A1, B1, then A1, B2, etc., and basically all these products of elements. So this will be a matrix with coefficients A1, B1, A1, B2, etc., up to A1, Bn. Now A2, B1, A2, B2, etc., A2, Bn, and all the way up to A1, B1, AN, B1, AN, B2, all the way up to AN, Bn. And this matrix must be a squared matrix. In fact, in quantum information, all the matrices are squared matrices. Yeah, and on the other hand, we already know that a matrix is some sort of a operator, right? Any operator is a matrix. Any matrix is an operator. We conclude that this outer product of two vectors, ket and bra, is a operator. Operator is an operator. And this is another important fact. This is very important for following. As I said, any quantity in quantum mechanics is described by operators, and this outer product of ket and bra gives me an operator. And let's check that, right? Let's take the arbitrary vector x, for example. It's not x. X is easy to mix up with this x of the ket bra product. So let's take y. So let's take any arbitrary y vector, and let's apply this operator on this vector, right? It's a operator, so we can apply this operator can act on any like vector in this from this space, from this linear space. So we write this we write this operator a b ket bra operator, and it acts on a vector y, any arbitrary ket vector from the space. Again, we don't write the things like this. We write it this way. So it is equal to ket, then bra, and then this vector y. But on the other hand, now I see that, oh, this is actually, this part is actually inner product of vector b and vector y. So this is vector b, vector I product, inner. And I can rewrite this as a two parts. This ket vector times this bra ket inner product. But we know that inner product, let me shift it here. But inner product is a constant, some constant, let's say c. So the result of this operation of acting of this operator, ket bra operator, is simply a constant c. It can be a complex constant times the ket vector a. So you can see that the action of this operator is simply the vector. So this operation creates the vector from the same space. That means that this is the linear operator from my vector space. So I guess this is a very good point to stop. Again, let me briefly recap what we learned today. So first of all, any matrix corresponds some sort of operator in a linear space. A operator takes a vector and changes this vector somehow. It rotates the vector, it makes it shorter or longer, deforms the vector, right? And vice versa. Any operator can be replaced by its matrix, corresponding matrix. And one particularly important case of matrices is the Hermitian matrix. Hermitian matrix is a matrix that coincides with the Hermitian conjugation operation. Hermitian conjugation is the transverse and complex conjugation. So this matrix, this type of matrix is important because its eigenvalues are real, and we can use this matrix to build up the quantum mechanics. Then we discuss basically how to find the eigenvalues of any matrix. Then we like recalled the matrix operations, how to work with matrices, how to multiply the matrices, how to find the inverse matrix. And the concept of inverse matrix is important because it allows us to construct the unitary matrix or check if the matrix is actually unitary. And the concept of unitary matrix is extremely important, is crucial for the following. That's why I guess next time we will solve a couple of examples with these unitary matrices, simply because unitary matrix is a rotation of a vector or rotation of the basis without the deformation of the space, without deformation of the vector. So it's just rotation, and just rotation keeps the vector, the length of a vector, or and the scalar product of two vectors unchanged. And in fact, all the physics of quantum basically world, the quantum mechanics, quantum computing is all based on using unitary matrices. And then we discuss the example why the rotation matrix, for example, rotation matrix in our real space is unitary. And then we introduce this bracket notation, which will be used like heavily throughout the course, because this is basically the alphabet or the language for quantum, for all quantum theory. This ket bra vectors, and then we say that outer product, the inner product of ket and bra gives you the scalar. It corresponds to the like any inner product of two vectors, something that we already discussed many times. And the outer product of ket and bra, it gives you some sort of a operator with a matrix presented here. And this operator takes a vector, for example, here, and produces another. I made a mistake here. So it's not a y, it's supposed to be a here, right? So this operator took one vector and changed that vector to another vector. So this is indeed an operator. And this ket bra notation is the way how we represent any operator in this using this language. Do you have any questions? Yeah, as I said, this all might look pretty, you know, complex and maybe bulky, and it's just the matter of a little practice. So I suggest you to watch this lecture again, and by the next time we meet, I will do recap next time, of course, remind you all this, and then we will solve a couple of examples to memorize the things and master this matrix operator notations and how we work with them. So we will practice. And yeah, and this, by the way, I don't have time to discuss a last problem from your homework. So I will extend the deadline, and we will discuss that, how tackle the last problem from your homework next time. Yeah. So any questions for now?
No, Professor.
So if not, let me stop the recording.